All right, so in my opinion, what we're about to do is the most important derivation that you'll see in any science class that you take here at Radford. Um, the time-independent Schrodinger equation. So if you remember, as part of our proof that the traveling wave is a solution to the classical non-dispersive wave function. Actually, may not have seen this yet when you watch this video, depending on whether we've worked this problem in class yet or not. But one of the things that we showed is that the second derivative with respect to x of a wave function that is a solution to this problem is negative omega squared over v squared times the original wave function. That's a fairly easy thing to prove algebraically just by taking that second derivative. Since the time-dependent portion is unchanged by the derivatives, the time-dependent portion drops out of the equation. In other words, since this equation on both sides has x-dependent times time-dependent, we can divide both sides by the time-dependent portion and get a equation that depends only on x, only on position, and not on time. Now, as you'll remember, omega is 2 pi times the frequency, where velocity of a wave is frequency times wavelength. So the second derivative with respect to x of the wave function is 4 pi squared. We're just substituting these terms in over wavelength squared times the original function. Now what we can do is take these lambda terms, these wavelength terms, out by substituting in the de Broglie wavelength. So we'll put h over p in for the square of h over p in for lambda, and we get second derivative with respect to x is negative 4 pi squared times p squared, where p is momentum, over h squared. And remember, we defined h bar as h over 2 pi, so h squared over 2 squared pi squared is going to be h bar squared. So now we can say that the second derivative with respect to x of the wave function is momentum squared over h bar squared negative times the wave function. We know from physics that total energy is kinetic energy plus potential energy. So we could have some potential energy function, and then energy of motion is 1/2 mv squared, which we showed in class the other day is p squared over 2m. So p squared is the kinetic energy is 2m times the kinetic energy, where the kinetic energy is the total energy minus the potential energy. So we can substitute this in for p squared. And so now we have the second derivative of a particular equation with respect to x of the wave function is negative 2m, things that we'll know about a particle, over h bar squared, a constant that we know, times the total energy of the system minus the potential energy function, all times the original wave function. So what we can do there is divide both sides by this term, and so we'll say that negative h bar squared over 2m times the second derivative of the wave function plus, so we'll move the potential energy function over this side, plus potential energy times the wave function is the energy times the wave function. So look at what we do. We take a wave function and we do all these things to it. We take the second derivative of it, we multiply it by negative h bar squared over 2m, and then we add that to the potential energy function times the wave function, and we get some number times the wave function, and that number is the energy of the system. And this is the mathematics that was worked out by Erwin Schrodinger back in the 1920s. Now, he also worked out, and it was a bit more complicated, the time-dependent Schrodinger equation, we'll call it, time-dependent version of this equation. For example, for certain phenomena like IR spectra and some other things, UV-Vis spectra, the time-dependent terms don't drop out the way they did for the classical non-dispersive wave function. And so, with a bit more mathematical effort, we can derive an expression that calculates energy using the time-dependent wave function. And so it works out to I times h bar times the derivative of that wave function, the full wave function, with respect to t, gives us the same equation that we got, that is energy times the wave function. Now, just from a personal interest standpoint, it's fun to mention that Erwin Schrodinger presented these derivations and the solutions to these problems for the hydrogen-like atom, the quantum harmonic oscillator, the rigid rotor, so those are used for vibrational and rotational spectroscopy, and a diatomic molecule in 4 papers that he published in the first few months of 1926. He did all this work and wrote all these papers while staying in a hospital, a sanatorium in Switzerland for a few weeks, because he was receiving treatment for tuberculosis. So he worked out all of the basic ideas of quantum mechanics in a few weeks while he was in the hospital for TB. So it's just very interesting notes, I guess, about his life. There's some other interesting things about him and his lifestyle if you want to look those up, or we can talk about them sometime. The equations themselves, the full time and x dependent wave function, as well as the x only, the time independent wave function, represent the amplitude of wave that describe a particle or a system of particles that we're working on a quantum mechanical solution for. To simplify derivations, we've only considered particles that can only move in one direction. Now, for systems like a hydrogen atom, we're dealing with a sphere. We're going to have to deal with 3 coordinates, and so we'll use a more complex coordinate system, but the same math basically works out. And so we'll work on those coordinate systems in a little bit later chapter. Now, when we say we're solving an equation, we're not usually doing that to calculate the energy. The energy calculation becomes very simple once we solve the equation. When we're looking for a solution to a quantum mechanical problem, we're looking to find what function, what wave function satisfies the equation and gives us that energy. So the difficult part, the solution, is the function. And so if we want to solve a time-dependent portion, typically we can separate the time-dependent portion and the time-independent portion in this fashion, time-dependent and time-independent. And then, like I said, we can calculate the energy of a system from the time-dependent portion by taking the derivative of that time-dependent portion with respect to time and multiplying it by I h bar. And so we can rewrite that to say that any function that's going to satisfy the Schrodinger equation has to be such that the derivative of that function with respect to time gives us negative I times E over h bar times the original function. That's just a rewriting algebraic shift of the previous equation. This expression is satisfied by an exponential that deals with this complex function, this complex term. So we can write any system wave function, time-dependent wave function, as the time-independent wave function times e to the negative I energy over h bar t. So this is a product of two functions, each depending on one separate variable. This is the same as we would see for the standing wave, because stationary states in quantum mechanics correspond to standing waves, going all the way back to Bohr's solution for the atom. Now, if we want to use the Schrodinger equation, what we've got to do is define a few new terms. An operator is a mathematical instruction or series of instructions that is to be applied to a particular function. In quantum mechanics, every observable has a corresponding operator. So we just derived the operator for energy earlier, and we'll show what I mean by that in just a moment. A function that gives a number times the original function when a certain operator applied to it is called an eigenfunction, and that number that's returned is called the eigenvalue of that operator on that function. So here's what I mean. Here's the time independent Schrodinger equation that we derived earlier. Negative h bar squared over 2m times the second derivative of the function plus potential energy times the function gives us a number, it turns out to be energy, times the original function. We could rewrite that by sort of factoring the function out of the whole left side of the equation and say that if we take this function and multiply it by the potential energy and add that to the function having been taken the second derivative of and multiplied by this term, we get the energy. Or everything that's inside of this set of brackets we refer to as an operator that we call the Hamiltonian operator, and that is the operator that returns energy for a particular wave function. Alright, so what we want to do is try out some examples. Pause the video right now, try this example on your own. Take a look at this function and tell us whether these two operators are, whether the function itself is an eigenfunction of those operators, and if so, what the eigenvalues are. And we'll work this out together in class. Two vectors are said to be orthogonal to one another if they are at a right angle to one another, or another way of saying that mathematically, if their scalar products are zero. The analogous expression for orthogonality of two wave functions of a quantum mechanical operator is to say that if those two different functions are multiplied by one another and then the integral is taken over all space, that we should get a total of zero for that if the two functions are different from one another. So the eigenfunctions of any quantum mechanical operator should all satisfy this equation, which brings us to another problem that you can try on your own. In order to use wave functions to calculate probabilities, the wave functions must be normalized. That means that we're saying that if these are both the same function, if they're different functions, we would get 0 in this case. If they're both the same function, we should get 1 in this case. And so together in class, we will normalize this function. We will take a times a minus x and make it so that the integral of the square of that function is 1 if we integrate it over this particular space that we're interested in.